In the last lecture, we looked at a plane parallel model for radiation. This is essentially a one dimensional model, but remember that in radiation, even in a one dimensional model, you have to account for all the rays traveling in all the different directions. So, if you recall, we started with the basic equation for radiative transfer, which was for a non-scattering medium. Which says that the change of intensity with distance is proportional to the emission by the gas and reduced by the absorption by the gas. Second term absorption, first term is emission. This is absorption coefficient, which has units of meter minus 1. This can be integrated, so that along a given direction you can get the intensity. But we are interested in fluxes, not intensities. So, we took a plane parallel model and we defined a normal and we looked at the angle theta. We assume everything is symmetric with respect to phi, the azimuth angle, and hence we from here related the intensity to flux by the following relation. So, this equation has to be integrated, and integration done in two parts. So, in this part, the upward going rays, that is theta between 0 and pi by 2 are all rays which are moving upwards, and so we had solved this equation for theta between 0 and pi by 2, and that one we called as I lambda plus rays moving upwards, and for the rays moving downward from the top, that is theta greater than pi by 2 and up to pi, we call it I lambda minus. We have to distinguish between the rays going up and rays going down, because the lower surface 1 here will only emit rays going upwards, and the upper surface 2 will only emit rays going downwards. So, when integrating this equation for upward going rays, we start from the bottom surface and go up, and when we look at the downward going rays, we start from the top, look at the emission of the upper surface, and we saw that there are 4 terms in the equation. 2 terms involve emission by the surface and attenuation in the gas, and other 2 terms involve emission by the gas upwards and downwards. And so, just to remind you, I will write the flux expression. So, the flux expression had 4 terms. So, the QR lambda, the net radiative flux between lambda and lambda plus d lambda consists of radiation leaving surface 1 and it is attenuated in all direction minus radiation leaving surface 2 minus because it is downward going rays, and the difference between the total optical depth. So, this is 0 and this is kappa lambda 0, and any location here is kappa lambda. The distance travelled here for the second one is kappa lambda 0 minus kappa lambda, while for the rays going up it is just kappa lambda. So, these are the two terms which represents the boundary contribution from emission and reflection by the boundary, which then moves through the gas. Then there are two more terms involving gas emission. The first is from upward one, it's equal to 0 to from here to here, all the upward emission, and it involves the black body emissive power of the gas times a function which represents angular integration. And the last term is again minus the downward emission by the gas between this point on the top, and that involves so this is the contribution from the surface 1, this contribution from all gas elements between this surface and kappa lambda. This is our where we want to calculate the flux. This is the downward emission surface 2. This is downward emission by all gas elements between kappa lambda and kappa lambda 0. Now, you should look at the argument here. You can see that we have written this such that is always positive. This is by convention that the argument here has to be always positive. So, in the region between 0 and kappa lambda tilde has to be less than kappa lambda. So, you write it this way. In the second term, kappa lambda varies between kappa lambda 0, therefore, it has been reversed, kappa lambda remains kappa lambda. Okay. So, this is an expression which we are going to use a lot. In this expression, there are two terms called the exponential integral functions, and the general definition is E n of x is equal to 0 to 1 mu to the power of n minus 2 e to the power of minus x by mu d mu. So, this accounts for all the angular integration that one has already done, and these are well tabulated functions available in books on radiation transfer, usually in the appendix. So, you can look it up anytime, and in today's world this can be computed fairly easily by any software. So, what we have done essentially is, in problems in radiation transfer, there are three levels of integration involved. You have to integrate over angle, you have to integrate over wavelength, and you have to integrate over space. So, we essentially have separated these three actions. The angular integration is built into this function E n of x. Spatial integration is involved here in this equation here, and we need to do somewhat later the wavelength integration. The major challenge we face is not the angular integration. That is very straightforward, as I said, can be done by any computer very easily. The major challenge we face in solving the equation is the fact that if you want to know the temperature distribution of a gas in an enclosure, then the unknown temperature variation is inside the integral here. So, this is a peculiarity in radiant heat transfer. In both conduction and convection heat transfer, you encounter differential equations. and there is a large repertoire of techniques available to solve differential equations of many kinds. So, that whole methodology is used very effectively in solving a large number of problems in conduction and convective heat transfer. In radiative heat transfer in gases, the problem has been more difficult because unknown temperature does not appear as a part of a differential equation, but as an unknown initial integral. So, it is an integral equation here. So, we do not have as many techniques for solving integral equations analytically as we have for differential equations. So, most of the solutions that will be normally done will be numerical, but in subsequent lectures we will do a few solutions which are analytical, because analytical solution give you a great physical insight as regards what is happening in a given problem. So, although we will be dealing with fairly simple and somewhat not realistic real world situations, ideal situations, still we believe that these simple cases are very useful to help you understand the phenomena of radiative heat transfer. And the key point here remember is that because in this equation we have integral equation, essentially what you see here in radiation is something very different from either conduction or convection. Conduction and convection are governed by different equations, so that the temperature of a given region is influenced only by the temperature of the surrounding regions, immediate surrounding regions, and that is why we are able to write everything in terms of derivatives in a different equations. On the other hand, in the case of radiation, the temperature in the middle of a gas in enclosure may depend on what is happening at the wall, because some of the photons that is emitted at the wall can go right through the medium without being absorbed and directly interact with the region you are concerned with. So, this could be thought of as action at a distance. So, so radiation problems are essentially non-local in character, that is, temperature of a given region is influenced not only by the temperature of the surrounding regions, it is also influenced by temperatures of surfaces or gases far away from the region of interest. And you will see that this equation, which is the more general kind, can be shown to ultimately become a differential equation in certain limits. So, this formulation is very general, and when we take some limiting case, limiting condition, then we will show that this equation can become like an equation in conduction heat transfer. But the real world situations which we encounter in radiation, is furnaces or the atmosphere or in metallurgy, we do not always have a situation where we can convert this to a differential equation. So, we must know how to solve integral equations, and so we will illustrate a few examples in the next few lectures, so that you are familiar with the techniques of solving integral equations. But you must realize that these are only two teaching tools to enable you to understand the phenomena. When you solve any real world problem involving radiation, you will solve it numerically. So, so the entire power of high speed computing can be brought in to solve fairly complex radiation transfer problems. Those are solved by large software packages, but those will not give you any real insight into what is going on in this radiation phenomena. So, we need simple analytical solution just so that you appreciate what is going on in this mode of heat transfer, in contrast to either conduction or convection. So, I want always for you to compare the way in which radiation transfers heat. With that, you already know what occurs in the case of conduction or convection. Now, before we go further to solve the equation, we not only need the flux, we also need the divergence of flux, because all of you recognize that the divergence of the flux is what is important in solving for temperature variation in a medium, because ultimately you are applying the first law of thermodynamics, and in the first law of thermodynamics on the right hand side you have the divergence of all heat fluxes. So, that includes conduction, convection and radiation. So, ultimately we must know how does the divergence of the radiative flux looks like, and so we derive an expression. By differentiating this expression, we derive an expression for the divergence of the radiative flux, and for convenience we write as minus. We write a minus because minus the divergence represents the energy added to the system. So, each term on the right hand side that I am going to write now can be thought of as a term representing energy deposition or energy removal from the system. The first term is the radiation leaving surface 1 and absorbed by the gas. So, this is a heat addition to the gas due to absorption. The second term is energy leaving the top surface and reaching the level kappa lambda and being absorbed. See, these are two terms represent the gain by the medium on account of absorption of solar radiation. Then you have a term representing the gain from all other gas elements below kappa lambda. So, these are emissions by layers below the level kappa lambda, which are absorbed at that level, and similarly we have terms which represents all the emission by gas elements above this layer radiating downwards and absorbed by the layer. So, although I am not showing the detail of the derivation, you must be able to do this from the previous equation for q r lambda by differentiating by applying the Leibniz rule for differentiation of an integral, which was discussed in the last class. So, we have, after doing that, you will get the first term representing the absorbed radiation from the top surface, second term absorbed radiation from the bottom surface, third term absorbed radiation emitted by all gas layers below this layer, and the last term radiation absorbed by the layer of all the emission downwards, so the above kappa lambda, and finally you have the emission term. So, this is the important term. This represents the in the 4 pi directions how the radiation is emitted in all directions by the gas. So, this is the expression for radiative heat flux. Now, this is in the spectral domain. We want the total radiation. So, all of you know that the total radiation flux is 0 to infinity q r lambda d lambda, and therefore, one can write as this quantity integrated over all wavelength. So, ultimately quantity of gray data to us is this term minus d cut, that represents the energies, total energy added to the system by radiation. Now, this is a step which is the most difficult step in this whole procedure, because A lambda is a very complex function of lambda. So, this is what makes life very hard to integrate this, because a typical absorption band of a gas contains millions of lines, and you have to account for absorption each line and the lack of absorption between lines. All this had to be accounted for, and this is no mean task, and people have been at it for the last almost 100 years. This problem was first looked at by astronomers. In astronomy, absorption coefficient is not a strong function of lambda. So, in astronomy, they were willing to adopt a gray gas model, that is assuming A lambda is not a function of lambda. This does remove one complication, that is the integrated wavelength, but we still have to deal with angular integration and spatial integration. Now, our task here is now to understand so we go back to the divergence of the radiated flux and recognize the 4 absorption terms: absorption from the bottom surface, emission from the top surface, absorption or emission by all gas elements below a level kappa lambda, and absorption of radiation emitted downwards by all gas elements towards kappa lambda, and minus 4 E lambda is the emission term. Now, this equation is quite complicated, and the primary complication that arises, that I already pointed out, I will want to repeat that so that it is understood. The main problem is unknown is inside the equation, and that makes it very hard. Now, before we set out to give examples of how to solve this equation, we want to look at 2 limiting cases. Limiting cases are always good to look at, because they provide some insight regarding the behavior of the system, because when you understand the behavior of the system in certain limits, you better appreciate what the system does when it is not in the limit. So, the first thing we look at what is known as optically thin limit, that is the total optical depth is much less than 1. Now, this does occur in real world, because we take the atmosphere in which we live, it mostly contains nitrogen, oxygen and argon. All these 3 gases hardly absorb any radiation, and so all the radiation is absorbed in the atmosphere by minor gases like water vapor, methane and carbon dioxide. So, these are in such small amounts in the Earth's atmosphere that you can treat them to be in the optically thin domain. So, there are examples in real world where the medium is in the optically thin domain, and you can almost avoid the integration in this case. Now, if we take out the thin limit, following conditions are satisfied. One can show that for small values of kappa lambda, which is going to happen because this total value is less than 1. Now, that will imply that E2 of approximately to 1. So, this is a useful approximation in the thin limit. Essentially, it is saying that there is no absorption by the gas. The gas absorption is so weak and the dimensions of the enclosure are so small, because if you remember kappa lambda 0 by definition is 0 to L A lambda dx, and therefore, kappa lambda 0 can be 0, either if L is very small or A lambda is very small. So, in this situation, in most places in the enclosure, you can assume E2 is equal to 1. And if you do all that, you can show that QR lambda becomes and minus So, in the optically thin limit, both the expression for radiative flux and the expression for the divergence of radiative flux are very simple. In the case of radiative flux, you see no impact of the gas. So, the fluxes are being exchanged between V1 and lambda 2 without measurable deviation. The second expression shows that even up to the thin limit, there is some absorption of so this expression is the expression for absorption by the gas of the radiation leaving surface 1. The second one is absorption by the gas of radiation leaving surface 2, and what it shows is that in both cases the gas is so little absorption there in the gas that the intensity of radiation that comes to the layer kappa lambda is not affected by the passage through the medium, because the medium is very weakly absorbing. So, we have the absorption term and the emission term. Now, optical thin limit is not very common, which is understandable, because as I pointed out earlier, one of the features of the absorption coefficient is that it varies very strongly as a function of wavelength. So, if one wavelength, it will be very strongly absorbing, and just the adjacent wavelength, if you go to, it does not absorb at all. So, in dealing with these minor gases that are there both in furnaces and in the atmosphere, we have recognized the fact that thin limit is rather rare. Still, it is a very useful approximation, because we are dealing with essentially algebraic equations. We do not have either an integral equation. So, this is something which we can solve very easily. Now, to illustrate how this can be solved, I take the thin limit and ask myself what is dq or dx. So, to integrate the previous expression over lambda to get this. So, this expression becomes fairly simple. So, we are integrating our wavelength now. So, this is the first term. This is the second term and this is the third term. So, all you have done here is integration over wavelength, and ultimately this will be performed on the computer. Suppose let us assume that you had access to a computer and you did all these calculations for gas typical of furnace containing some carbon dioxide, some water vapor, and knowing their properties you calculate all this. Even if you do that, it will be useful to write this equation in a more understandable form. So, general practice is written as so this simple expression shows there are three absorption coefficients here called the Planck mean absorption coefficients. I will write down the expression for them for your benefit. The first expression is for AP1, then but similarly AP2, so each of these functions is weighted by the wavelength variation of the radiosity of the corresponding surface, and finally for the gas so the purpose of defining these three absorption coefficient, one for radiation coming to surface 1, one for the radiation coming to surface 2 and the third for the gas, is that in some situations these can be calculated a priori before you actually solve the problem. And so, once you have tabular values of AP1, AP2 and APG as a function of temperature, you can solve most problem that one encounters in this optically thin limit. Now, this limit is not that useful as I pointed out, because there are very few gases which satisfy the condition they are optically thin at all wavelengths of interest. That is very rare. So, there will be situations any certain wavelength, certain gases will absorb radiation strongly. So, you may be in a position to define the Planck mean coefficients and use it. Now, I must mention one more thing. The last quantity APG is a Planck absorption coefficient weighted by the black body function at gas temperature. This should really be called Planck emission coefficient. This is because this coefficient is weighted by the black body function at the gas temperature. So, it has all the required conditions satisfied to call it an emission coefficient. But historically this has been called absorption coefficient. So, that name sticks, but strictly speaking these two are absorption coefficient because they represent the integration over wavelength of the incoming radiation at 1, and there are 2, there could be very different wavelengths. So, you need to do them separately, but the Planck absorption or emission coefficient, the last term, depends both on the specific gas and its A lambda distribution, as well as the weighting function brought in by, in this case, as A lambda b. So, the thin limit is attractive still for certain applications, because this expression is a differential equation, and this expression can be plugged into the general energy equation, and there will be other terms, and this will be going along with them. So, some of those cases where people solve these equations, they will be extremely happy that the expression for the divergence of the radiative flux is fairly simple. If you know the temperature, the problem becomes even simpler, but normally temperature is an unknown, it needs to be evaluated. So, it does take some time to get that number done. Now, we can ask a simple example you can take to illustrate this. Suppose the system is in radiative equilibrium. But this will mean system for which the divergence of the radiative flux is equal to 0. This is a useful starting point, because if you look at the energy equation and assume steady state and neglect all other phenomena like conduction, convection and other phenomena, and focus on the radiation, then you do expect that in steady state, that is from the energy equation, in the steady state everything will be in equilibrium. So, if that is the case, then one can see from first law that the divergence of the radiative flux has to go to 0. So, for the case of the optic thin limit, this implies that the temperature of the gas in an enclosure in which you have invoked the optically thin limit will come out as a very simple expression for the temperature of the gas, because the equations are algebraic. So, all you have to do is to, from tabular information available in most textbooks in radiation, you calculate the Planck B mean absorption coefficient with the limit surface and surface 2, multiply them by the corresponding radiosity values, calculate numerator, and divide in the denominator by the accepted monthly mean radiation values. So, in principle, in optically thin medium, you can estimate temperature as function of x, y and z if you have information available on the right hand side, and if not, you should be doing other kind of computations which are much more demanding. Now, the next step is, after having defined the thin limit. So, notice that in the thin limit, the equation for radial heat transfer becomes an algebraic equation. So, it is easy to solve the equation either analytically or numerically. So, people would like to invoke the thin approximation. So, that instead of dealing with a full integral equation, you deal with a simple equation, it's all algebraic. Now, if you look at radial equilibrium condition, you can get the temperature. So, computing this is fairly straightforward, and values of the Planck-Pean absorption coefficient are tabulated. It has to be this has to be, slight error here, this has to be 4 APG. Okay. So, once you have an estimate of AP1, AP2 and APG, then based on the information of the radiosity of surface 1 and surface 2, you get the temperature in the gas. Now, you will notice that in this limit, G is not a function of x, and this is the peculiarity of the thin limit, and one can easily show that if this surface 1 and this surface 2 and surface 2 has at one temperature, let us say T2, and surface 1 other temperature T1, you will find the gas will have only one temperature and there will be two jumps. These jumps are called slips. So, what it says is that in the optically thin limit, the gas has a single temperature invariant with distance x, but at both the boundaries there is a change in temperature, that is the temperature of the gas at the boundary is not same as the wall temperature. So, there is a slip, and this is a very special feature of radiation heat transfer, which is not encountered that often in the case of conduction and convection heat transfer, in both of which it is normal practice to assume that the temperature of the gas next to the wall is same as the wall temperature. But this approximation is not valid for now. In this thin limit, the problem is becomes rather trivial, because the temperature is not varying in the gas, it is uniform, and there are two jumps which can be evaluated. And there are not many situations in the engineering practice where you might encounter this kind of condition. This may be partly true in small metallurgical furnaces, where because the furnace is small, its ability to absorb radiation from the walls is somewhat limited. But what I want you to notice is that from the radial equilibrium conditions, we are able to get temperature of the gas, but when you calculate fluxes, which is what we did first, in the case of fluxes, there is no influence of radiation. So, as far as radiative fluxes in this enclosure is concerned, they are unaffected by the presence of the absorbing gas, but when it comes to the divergence of the flux, they are prominently there and they have to account for. Now, this might puzzle some people as to how in the flux calculation you can neglect the role played by the gas, but in the divergence of the flux calculation, gas properties come into play in a prominent way. So, all you must remember is that ultimately whether you really take into account radiation or not depends upon the importance of radiation vis-a-vis other modes of energy transfer, that is conduction and convection. So, that when we took the thin limit and look at the derivative, those may have been small if the gas is awfully thin, but we must compare this radiative flux with that due to conduction and convection. Only then we cannot say these quantities are small and hence we can neglect it. We have to compare these quantities, however small, with the competing quantities coming from conduction heat transfer and convection heat transfer, and only then we can be absolutely sure that these terms are really small. Now, the next limit we considered is the optically thick limit. And the major feature of this limit is that the total path length is much greater than 1. So, this is exactly opposite of the thin limit. Thin limit, this quantity is very small. So, we could make very simple approximation, but now we are dealing with a case where this quantity is very large. Now, in this limit, if you want to look at the radiative transfer equation, you have to do a lot of work, because in this limit the expression you get is derivable, but not in a way that you have done for thin limit, where the problem became very trivial because you were able to essentially neglect gas absorption. So, now we have what we are going to propose in this limit is not only is the total optical depth much greater than 1, we also invoke the fact that we also will look at only those points which are having a high optical depth, which translates to the fact that our kappa lambda we are going to look at, the distance from the wall, are sufficiently far away from the wall that you can invoke the thick limit. So, when you get a thick limit, we will get a simpler equation, but remember that somehow you have to get the information about the value of kappa lambda. Without that, we can proceed further. Now, once you assume this, it automatically follows that this is also true. So, you have kappa lambda 0 much greater than 1, kappa lambda much greater than 1, and also kappa lambda 0 minus kappa lambda also much greater than 1. Essentially, what he is saying is that in the two parallel plates, I am confining myself to the interior and not going too near this wall or this wall, because if I can go near a wall, then I am going to violate the condition of optical thick limit. Once you have done that, in the optical thick limit, remember the photon mean width was very small. L, that is between the plates. So, photons are getting absorbed very quickly over a very short distance compared to the distance between the plates. So, in that limit, the gases in the interior will only see adjacent layers from there the emissions are occurring. They will not see the two walls because they are very far and the radiation emitted wall is absorbed right next to the wall, and so the elements which are in the interior do not normally see the two walls. Okay. So, that being the case, we can expand the black body function that we encounter in the integral equation, which is the most difficult one, in terms of local value and a derivative. So, this experiment I am going to do of the emission by a gas element at kappa lambda delta in terms of the emission at kappa lambda and the derivative of this quantity evaluated at kappa lambda. So, this information is plugged into the equation. In addition, because kappa lambda 0 is very large, we can say that E3 of kappa lambda for kappa lambda tending 0 is approximately equal to half. That is E3 of 0 is half, we know that. So, we assume it is approximately equal to half. Similarly, we talk about, I am sorry, this is 0, I am sorry. Because it is very large, sorry, kappa lambda 0 is very large. This quantity tends to 0. Same thing is true of E3 of kappa lambda 0 minus kappa lambda, it also tend to 0. So, that means you are far away from the two walls, and so the radiation from the two walls are attenuated so much that you do not see it. And the approximation I mentioned in the previous slide now will lead to the following expression for q lambda. It will be equal to now, I want to notice that many of these will come, this will go to 0, this will go to 0 because that is what I assumed, and these two will add up. Sorry, these two will also get cancelled out, half and minus half. So, these two expressions will not be there, both are gone, 2 of them because they are small, these two because they are cancelling. So, you will be left only with two terms involving gas radiation, which is QR lambda is approximately equal to the two expressions representing gas emission. Now, in the limit which is optically thick, this goes from 0 to infinity. This can also be rewritten in terms of kappa lambda 0 minus kappa lambda to make go 0 to infinity, and using the fact that 0 to infinity x E2 of x is equal to 2/3, can simplify the expression to write the following very simple and elegant result, which is radiative heat flux is equal to minus 4 by 3 d E lambda b d kappa lambda for thick limit. This is a very useful and powerful result, because we have converted the basic complicated expression for radiative flux, which was an integral equations, into a differential equation. This has happened because the photon mean free path is much smaller than the length scale of interest to us. So, that means that photon hardly travels any distance, and so everything is controlled locally, and the local gradient plays an important role. So, this what happens also in conduction and convection, which many of you have studied, and so we will continue this discussion in the next lecture, and we will show how this result is a very useful result. Although you do not encounter many situations in engineering wherein either thin or thick limit is actually valid, but still these limits provide insight about the nature of radiation heat transfer. Thank you.